Okay, so the last video we went over how to write electron configurations. We went over two different methods, the longhand version and the noble gas version. There's one more type of electron configuration that we need to go over, and that's orbital diagrams. So I'm going to pull up my whiteboard here. And first off, an orbital is giving us a little bit better idea of where the electron is located. Okay, so the orbital is another little subdivision in the sublevel. So we have the energy level, which is this big idea, big city where we live. Then we have a sublevel, which could be a street, for example. And then we have an orbital, which is like your house number. So the orbital is contained within the sublevel, and it gives us like a probable location of the electron. And each orbital can hold a max of two electrons. And when we draw our orbital diagrams, we're going to represent an orbital with a line. Just like that. Now, since each orbital can hold up to 2 electrons, the different sublevels have a different number of orbitals. So our sublevels, remember, those are going to be S, P, D, and F. Since an S sublevel can hold up to 2 electrons, an S sublevel is only going to have 1 orbital. A P sublevel can hold up to 6 electrons, so it's going to have a total of 3 orbitals. A D sublevel can hold up to 10 electrons, so it's going to have 5 orbitals. And an F sublevel can hold up to 14 electrons, so it's going to have 7 orbitals. Okay? When you write your electron configuration, your orbital diagrams, you're always going to want to label your sublevel, such as 1s, and then draw a line. And then your 2s, and then a line. And then your 2p, and you would have 3 lines because p sublevel can have 3 orbitals. Okay? And I'm going to show you how to fill these orbital diagrams here in just a second. So there are 3 rules that we have to follow when we are drawing our orbital diagrams. Those rules are the off-ball principle, which says we have to fill the orbitals from low energy to high energy. And this rule you already can follow because if you read the periodic table the way that I just showed you, if you read it from, left to right, top to bottom like a book, you are filling your orbitals in order from lowest energy to highest energy, okay? The next rule is going to be Hund's rule, and that says that we need to singly occupy orbitals before doubling up. So this does not affect the S sublevel because it only has 1 orbital. When you look at P's, D's, and F's, because they have 3, 5, and 7 orbitals, what Hund's rule is saying is that we want to make sure that there is 1 electron on each line, so 1 electron in each orbital before we go back and put that second electron in, okay? Then our last one is the Pauli exclusion principle. Can't type. And this says that electrons in a doubly occupied orbital need to be of opposite spins. So when we are drawing our orbital diagrams are going to have lines to represent the orbitals, but then we're going to have arrows to represent the electrons. So in a doubly occupied orbital, you would have 1 up arrow and you would have 1 down arrow to represent opposite spins. These electrons are all negatively charged, so they all naturally repel each other. So when you fill in an orbital diagram, it fills from lowest energy to highest energy and singly occupy the orbitals in order for the electrons to get as far apart from each other as possible. And that reduces the energy that's associated with that electron arrangement around the nucleus, okay? So when we look at carbon, for example, carbon is 1s, 2, so we're going to put 2 electrons in the 1s. It's 2s with a single line to represent a single orbital, 2, so we put 2 electrons in there. And then it's 2p2, so we have to have 3 lines because it's a p sublevel. And with it's 2p2, we're going to put 1 up arrow in the first 2 orbitals because of Hund's rule. We need to singly occupy the orbitals before doubling up, okay? When we look at sulfur, for example, sulfur is 1s, 2, so we have 2 arrows. It's 2s, 2, so we're going to have a 1 up and 1 down. And then it's 2p, 3 lines. And notice I'm going to put all of my ups first, and then I go back and fill the downs. I really encourage this practice because you're going to get to the place where you're not going to have it all fully occupied. If you're in the practice of putting all your up arrows first, you know you're always going to follow Hund's rule and singly occupy your orbitals before doubling up. After 2p6 in sulfur is 3s2. So that means there's 2 electrons. And then it's 3p, so I have to have 3 lines, 3 orbitals. It's 3p4, so I have to have 1 up, 1 up, 1 up, and then 1 down. Okay, so that's sulfur's orbital diagram. Let's say that we have gallium. Okay, gallium is 1s, 2, 2s2, and sometimes it might be easier for you to write the electron configuration first until you get used to it. 3s2, 3p6, 4s2, 3d10, 4p1. So when you draw the electron configuration, the orbital diagrams, you have 1s, a line, 2 arrows. 2s, a line, 2 arrows. 2p, 3 lines, 6 arrows. 3s, 1 line, 2 arrows. 3p, 3 lines. 6 arrows. 4s, 1 line, 2 arrows. 3d, 5 lines. All of my ups first, and then I'm going to go back and do my downs. And then it's 4p, I need to have 3 lines, but just 1 has an electron in it. The other 2 are empty, okay? Now, how many valence electrons does gallium have? And this is purposely why I picked gallium. Okay, so look at your energy levels. The energy level that's furthest away from the nucleus is going to be energy level 4, because we have a 4s and we have a 4p. These 3ds, those are not valence electrons because they go back and fill the 3rd energy level. So gallium has 3 valence electrons because of the 4s2 and the 4p1, okay? When you're drawing your orbital diagrams, again, make sure that you're putting your sublevel, such as this, 4s, 3d, 4p, for example, and make sure you are drawing your lines to represent your orbital diagrams. And just let me know if you guys have any questions while you're drawing your orbital diagrams. Good luck!